Steel Dynamics is a leader in the mini-mill steel-making industry with a focus on value-added products with demanding quality requirements. Our core purpose is to harness the American spirit of hard work and innovation to build a better future. Our mission is to provide our customers a lower total cost of ownership through safe and innovative manufacturing excellence. And at the heart of the mini-mill process, a more environmentally friendly way of making steel is scrap steel. Lots and lots of scrap steel. In fact, over 90% of the material SDI uses to make new prime steel consists of scrap steel that has been reclaimed from end-of-life infrastructure, factory machinery, agricultural equipment, automobiles, appliances, material that was often left to rust in junkyards or litter the countryside. Environmental issues are a concern for all of us, and no one in the steel industry is doing more to help the rail transportation industry than Steel Dynamics. Regardless of the product, our recycled content, a critical issue for LEED certification, runs in excess of 75%, and in most cases considerably more. SDI also owns OmniSource, the second largest scrap recycling company in North America. And that's where our story begins, at an OmniSource facility in Indianapolis. OmniSource collects and processes ferrous scrap and non-ferrous scrap at more than 70 facilities around the country. Here at one of OmniSource's 5 facilities in Indianapolis, a gigantic shredder reduces entire automobiles and other large pieces of scrap into smaller sections that will fit into our electric arc furnaces. After the scrap is shredded, giant magnets separate the ferrous materials from the non-ferrous. Non-ferrous scrap is conveyed away for further sorting. Just as in the mini-mill steelmaking process, nothing goes to waste. At a visual inspection checkpoint, employees remove any non-ferrous scrap that's hung up with the ferrous material. Some of that ferrous scrap is destined for our rail-making facility near Columbia City in northeast Indiana. We began shipping a significant volume of standard strength American Railway Engineering and Maintenance of Way Association, or AREMA rails, in 2010, after our products gained certification by all Class I railroads. Our rail production capabilities are unique to North America. We produce rail in lengths of 320 feet, which can be shipped in this long length, cut to shorter lengths, commonly 40 or 80 feet, or welded together to create long rail strings of up to 1,650 feet. We currently have the annual ability to produce 350,000 tons of AREMA standard rail sections in 115RE, 136RE, and 141RE weights. The mill campus includes 15 miles of railroad track capable of handling 700 rail cars at one time for incoming scrap and outgoing steel shipments. The mill also receives 200 to 300 truckloads of scrap and other raw materials every day. It's a 24/7 operation that runs 365 days a year. 3 30-ton scrap cranes and large front loaders facilitate moving the scrap around, in and out of rail cars and trucks, and to the scrap bay at the edge of the melt shop, where large magnets lift up the scrap and place it into a charging bucket. Scrap is loaded into the charging bucket according to grade to achieve the exact chemistry necessary for our steel products. Each furnace heat consists of 120 tons, with over 90% of it scrap. Many mills use electric arc furnaces, or EAFs, which require much less in the way of natural resources versus traditional blast furnaces. For every ton of steel produced by SDI, we eliminate the need for 2,500 pounds of iron ore, 1,400 pounds of coal, and 120 pounds of limestone, and we use significantly less energy in the process. The EAF process also produces 67% less carbon equivalent emissions. In addition, 95% of our scrap comes from within 250 miles of our plants. The charging bucket is moved to a position directly above one of the mill's two EAFs. The scrap is then released into the furnace, creating some real fireworks. The reason for the explosion is that a portion, about 40 tons, of each heat of molten steel is left in the furnace to keep it hot for the next heat, saving time and money. The roof of the furnace is closed, and 3 large carbon electrodes are lowered through an opening in the roof. Then, it's showtime. And it's loud, very, very loud. The rods circulate or arc up to 115 million watts of electricity to melt the scrap at a temperature reaching 3,000 degrees Fahrenheit. The power is on for about 35 minutes to complete the melting of each heat. Once a heat is completely melted, the furnace is tipped to pour off the slag, a collection of impurities that rises to the top of the heat. Here again, nothing goes to waste. The mill sells more than 200,000 tons of slag each year. Slag's primary use is as a substitute for mine gravel. Molten steel is then tapped through the bottom of the furnace and into a ladle. The steel then goes to the ladle metallurgy furnace, or LMF, where a variety of processes can be accomplished, including desulfurization and deoxidation. The temperature of the steel can be adjusted with carbon electrodes, and the chemistry of the steel can be changed by reducing some alloy elements and the introduction of others. The steel is also mixed using argon gas to ensure uniform temperature and composition throughout the entire heat. In the next step, the ladle of molten steel is placed in the vacuum tank degasser, where hydrogen is removed from the steel, a process that keeps the rails from becoming brittle. Here, the lid is placed on the ladle prior to degassing. After being removed from the degasser, the ladle is placed on the casting turret and rotated into casting position. In the first part of the casting process, the steel is released into the tundish, which has specially designed submerged entry nozzles or SENs that create 4 strands of steel. Here, a special hydraulically driven oscillation system moves the molds up and down to prevent them from sticking to the caster mold walls. At the bottom of the casting machine, the strands, now called blooms, are cooling and solidifying. At this stage, the blooms are 10 by 14-inch rectangles. Here's a look inside the casting control pulpit, where operators carefully monitor all the casting parameters. These are the soft reduction units, where the blooms are withdrawn from the casting machine and precisely squeezed a few millimeters to eliminate carbon segregation in the center. This process is one of the key factors that separates us from other domestic rail makers. Automatic torches cut the blooms into sections that are approximately 33 feet long. At 460 pounds per foot, each bloom weighs in at 7.5 tons. Next, the blooms go through an automatic metal tagging machine. Each bloom receives a tag with a barcode that includes important information, such as the heat number, which of the 2 casting machines produced the bloom, and the date produced. The blooms are then picked up and placed in the reheat furnace, reheated to more than 2,000 degrees Fahrenheit. The blooms are now soft enough to be shaped into rails. The discharge machine takes the blooms from the reheat furnace. After exiting the reheat furnace, blooms go through a descaling machine to remove oxide scale created during reheating. The scale is removed with water jets spraying 4,000 gallons per minute at 3,000 pounds per square inch. In all, we use nearly 200 million gallons of water per year to operate and cool our processes. That water is recycled on-site and reused. Next up, the blooms enter the breakdown mill, a one-stand reversing mill driven by a 7,500 horsepower motor, where the rectangular blooms undergo 11 passes. Leaving the breakdown mill, the rails are now half as long as the finished section they become. The 3-stand reversing tandem mill comes next. Here in the pulpit, operators control and monitor the final step in turning blooms into rails. In the tandem mill, automatic gap control technology constantly adjusts the gap between the rolls to maintain a tolerance of 10/1000th of an inch. The ends of the rail sections are rough cut with a saw before the sections go onto the rail cooling bed, where the temperature of the rails is reduced to less than 200 degrees Fahrenheit. The newly produced rail is straightened vertically and horizontally as it goes through 2 rotating straightening machines. The rail now undergoes the first of several non-destructive tests. First, at the profile measuring station, critical dimensions are tested. Next, geometric testing is done to ensure the flatness of the rail, and then the rail is visually inspected. Next, the eddy current system automatically inspects critical rail surfaces by introducing a small magnetic field into the roll. An interruption of the magnetic field as it passes through the rail would indicate the presence of a flaw. Last, ultrasonic testing is used to ensure internal soundness of all rails. The ultrasonic system can detect flaws smaller than the current ARIMA specifications. After the rail passes inspection, the cold saw cuts the rail into 320-foot lengths before it goes to the welding facility. During this step, samples are also taken for offline destructive testing. A final laser check measures the end straightness of the rail sections to the last 3 feet. This step ensures that the ends of the rail sections are ready to be joined with other rail sections in the rail welding facility. A specially designed crane system in the state-of-the-art rail finishing facility lifts 5 320-foot rail sections at a time and places them on a rail car for transfer to the rail welding facility. Concurrent with preparing the rail sections for transfer to the welding facility, the samples taken at the cold saw undergo a series of stringent destructive tests that include the use of a scanning electronic microscope to perform metallographic analysis, ensuring the internal cleanliness exceeds specification requirements. After receiving final approval during destructive testing, the 320-foot rail sections are joined in the rail welding facility to create rail strings as long as 1,650 feet. By incorporating 320-foot sections to make longer strings, we minimize the number of welds needed from the traditional 19 welds to just 4. The method used is flash butt welding, which doesn't incorporate wires or other material to form the bond. Electricity is passed through both rail sections to create a bond almost as strong as the rails themselves. Each weld is accomplished in about 5 minutes. After welding, the rail strings undergo finishing to remove flashing and then are transferred to our quarter-mile-long rail storage facility. Welded rail sections are shipped by train to our customers on special car configurations that accommodate the quarter-mile-long strings. As part of our commitment to provide our customers with the highest quality products and services that meet their challenging requirements, our rail production facility also offers a state-of-the-art heat treating system that produces premium rail. Our goal is to become North America's preeminent rail manufacturer. Heartland-made rail from Steel Dynamics, an efficient, cost-effective, environmentally sound way to move people and products, and to keep all of America moving forward.